Let's discuss transformers. This is a very practical application of what we know about the magnetic coupling of circuits. Just to be very clear, by a transformer I don't mean one of these. This is an application of what we know about self-inductance and mutual inductance. And just to remind you what a transformer is, it's a device for stepping up or stepping down the voltage of an alternating electric signal. If you don't think transformers are important, try to live without them. Just one example is they're needed and necessary for the transmission, distribution, and actually use of AC electric power. So the transmission would involve, say, over long distances. So the basic circuit of a transformer involves two parts. There's the part where you have the source of EMF that's driving everything, and that's called the primary circuit. And so if you have this oscillating voltage here, you would have a current that also oscillates through this coil here. Let's let N1 be the number of turns that are contained in this primary circuit. There's a secondary circuit which also has a coil with N2 windings. If you had a load across these 2 points right here, you would have a current that is generated because of the closed circuit. If you have no resistor or load across here, then there's no current. There will, however, be a voltage. So there's an open circuit EMF that's generated across these two wires. To look at a usual transformer, you have these windings sharing a core of magnetic material. And we'll talk a little bit about that. Okay, so one more time. This is the primary circuit with the source of the power and the EMF that's going to drive this. You have a secondary circuit, which is basically where you're going to dump the energy into some kind of a load here. Just to remind you, we're using inductance only to couple these two circuits. So there's only a magnetic connection between the two. There's no wires that connect this one and this one. Just to repeat, it links the two circuits inductively. Like I said, in real transformers, these are coils that are wound onto some sort of magnetic material, say a soft iron core. This core, on purpose, has no permanent magnetization. So remember that if you have the magnetization M, which would be time dependent, would be proportional to H as a function of time, which remember H is proportional to the current. The magnetization is switching back and forth if we have an alternating current, and that's helping us get this coupling. The purpose of this core is to channel the magnetic flux generated by this primary circuit over to the secondary circuit. The core helps you link these two together efficiently. And if you want the maximum power transfer, the minimum losses, you want these two coupled very, very strongly. Well, we're going to take a simple example. I've redrawn a set of coils that we've used before, but we're going to pull this one out, this one this way, and we're going to let the radius go out this way. So what I'm really saying is we're going to have two coils that are very, very close to each other, and the only difference between them is the number of turns. So here we are, two solenoids. They're going to be the same length L and the same radius. So you can imagine these being really thin wires so that you're allowed to do that. And the total number of windings will be N1, which is little n1 times L, and N2, which is N2 times L. While we derived M before, if we look at M in terms of the parameters that we have here, we have mu0, N1, N2. Here's the area, and that's the same for both of these coils times L. So you can rewrite that in terms of the capital N's. So N1 over L, N2 over L gives you little n's. And then remember you have an L here, so that cancels this L squared to give you an L down here. And so you're left with the mutual inductance in terms of the total number of turns in the two windings times pi a squared because they share the same area. With the same radius, all of the flux from one current, let's put the current into coil 1, so we'll have I1, couples to the other coil 2. Remember, this is what we call phi sub 2, By definition of the mutual inductance, the flux in 2 due to 1 is what we called M12 times I1, but remember M12 is just equal to M because M12 is equal to M21. So let's take a function for V1. Let's let it be a cosine function. So we can write it as V1 is equal to a capital V1 times cosine omega t. So that's an oscillation that has omega being the angular frequency and V1 would be the peak voltage. For a pure inductance load, so we have an effective L, we would have V1 equal L1 di1 dt. So what we're saying is that we have this primary circuit, so here's our coil and we have this source of voltage here. That the first thing to think about is the fact that if we have an effective inductance here, then the voltage will be equal to the value of L times the derivative of the current that's flowing through the coil. Well, you can solve this for di, so it's V1 over L1 dt, and then substitute in our V1, which is V1 cosine omega t dt, integrate, and so you end up with the current I1 being sinusoidal also, but with the sine function compared to the cosine function. So there's a phase shift between the current and the voltage. If I1 is the peak current in the primary, the I1 generates a changing magnetic flux in the core of the solenoid, which links the secondary coil, and this generates inductively an alternating EMF V2, and again this will be an AC EMF and it will be phase shifted with respect to I1. If we take our V2 to be V2 times cosine omega t in the secondary circuit, and V2 is the peak voltage of little v2. So we suppose that this EMF drives an alternating current I2, and it will also be given by I2 sine omega t, just like we had for I1. In order to get this current, we have to have some connection between the two ends of the coil in the secondary. Quite often we'll just assume that it's a resistive load. So here's our repeated functions up here. We have the V1, V2, and the I1, I2. We'll assume that in the actual coils of the transformer there's no resistance. So if we just take a look at the primary loop, there's no resistance, and the circuit equation for the primary circuit, so that's this circuit over here, is the potential that's driving everything. It will be minus the potential due to a time-dependent current and the self-inductance, and then there will be a term that will relate to the potential due to the induced current in the secondary. We have the first term, the external potential that's generating all the currents. This is the back EMF due to the self-inductance in the primary coil. The last term is the EMF due to the mutual inductance of the primary and secondary coils, that's the M. This would be the potential, the back EMF in the primary due to current in the secondary. Okay, so if you sum all of those are the only sources of potential, that will be equal to 0. So you've gone around the whole loop. Looking again, this is the same equation. Putting in the time dependence for these functions, we'll have that the V1 is the cosine function minus L1 times the derivative of the current, and we've already written that down here. And then we have the derivative of the I2 current, which is right here. Okay, so where did I get those? Well, that's these functions up here that we've written down before. The sum of all of these is still equal to 0. And realize all of this is wiggling the frequency omega. When you take these derivatives, you get cosines in both this term and this term. We can factor out the cosines. And so that would lead to an equation which only relates to the peak values. So this is the peak value in V1, peak value in I1, peak value in I2. And so that's a relationship that just has the amplitudes of those oscillations, and there's no time dependence in this equation. So what about V2? Well, that consists of the EMF generated by the self-inductance L2 of the secondary coil, the EMF generated by the mutual inductance M of the primary and secondary coils. Just like the primary loop, we can obtain an equation for the secondary loop, and it looks very close to what we had before. So we have the back EMF in the secondary loop now. Here's the potential that goes to the load, and then there's the term dealing with the mutual inductance, and this time it's the change in I1 that is leading to a back EMF in circuit 2. And the sum of that, if we go around the loop, is equal to 0. So again, we put in our sinusoidal functions. Here's cosine for the voltage, here's sine derivative with respect to time of I2, and the derivative of I1 with respect to time put here, and so we have the entire loop equaling 0. Again, we have a cosine omega t common to all these factors, and so that leads to another equation which is just the amplitudes, no time dependence here. That will give us a second equation that we'll be able to use. Now let's look at the power. The power on an instantaneous fashion, so this would be if we have the factors, the cosines and sines and so on, into the equation for the instantaneous power that's being supplied to the primary circuit. That's just equal to I times V, and remember this is a sine function, this is a cosine function. Likewise, there's power transferred inductively from the primary to the secondary. So if we have a load, we'll have an I2, and so the power that is delivered to the secondary will be this quantity here, and that's the power that's going to be dissipated in the load, which is, say, a resistor R. The value of R will certainly have an influence in I sub 2. If we're going to conserve energy, if there's no resistive losses in the transformer itself, so the primary and secondary circuits, we can still have a load, but that's outside. Energy conservation says that these two powers must be equal. That's for all times. That said, then we can set these two equal to each other, put in the functions with amplitudes and the oscillating factors. So then we'll have I1 sine omega t, V1 cosine omega t on one side. Then we'll have the same thing with the two subscripts over here. Well, notice that you have a sine, cosine, where the time dependence is. Those cancel, and so you're left with again an equation for just the amplitudes. And so the peak values of I and V are conserved. So you have the peak value of the voltage and current in the primary equal to the product in the secondary. If we go back to our equations for V1 and V2, so I just rewritten them here, in terms of the inductance and the mutual inductance, so this would be the self-inductance, then we can substitute that in to the I1 V1 equals I2 V2. So we just put those in. We're multiplying it out, so I1 goes here to give you a square, then there's I1 I2 here, and likewise on this side we have I2 squared, and then I1 I2. What happens, of course, is that this term here cancels this term here, because they both have I1 I2 in them. The omegas cancel, and so you're left with this expression right here. The Li squared is equal on both sides. So we can solve this for the ratio of I1 to I2, and that will be equal to L2 over L1 square root. We can do the same thing for the voltage, so using this equation here and the ratio of I1 to I2, we'll get the ratio of V1 to V2 is equal to the flip of the current. So this will be L1 over L2 square root. Notice that these two equations have no M dependence. It only depends on the self-inductance. So the mutual inductance M of the two coils, which is entirely responsible for the transfer of energy between the primary and secondary circuits. Okay, let me repeat. The mutual inductance of the two coils is really what causes the transfer of energy between the two circuits. But it's the self-inductances of the two coils, L1 and L2, which determine the ratio of the peak voltages and the peak currents in these circuits. But don't forget, L1, L2 is related to M. In a sense, the mutual inductance is still involved. So using our ratios, this is I1 to I2, and here's V1 to V2, we can now use the equations for the solenoids. The reason we are doing this is because we want to have a case where we can get simple relations between the number of turns in the windings and these potentials and currents. So we start with just the ith coil, so I is just going to be 1 or 2. And so this is what we derived before, where we assume that for a given I, we have the same area and the same length, which is the way we set up these two coils. Given this general equation, we can put in 1 and 2. So here's our L1, L2, and that's going to be equal to, here's L1, so all we have is this 1 here. Here's L2, so we have the 2 here. All but the n's cancel out. So this ratio here is N1 squared over N2 squared. So if we go back to our expressions for the ratios of the currents and the voltages, we can see that the V1 to V2 is equal to N1 over N2, and the currents are reversed. It's N2 over N1 for I1 and I2. Well, we can solve this for V2 and for I2. As you imagine, you flip the n's. And so you have V2 is equal to V1 over N2 over N1, and I2 is the inverse of that ratio times I1. So we have a pretty good description of what's going on here in terms of the winding number determining how these voltages and currents change. The ratio of these numbers of turns determines those relationships between the voltages and the currents. So these two sets of equations, or all of these equations, really dictate how the transformer is going to behave and perform. The one thing that I want to make sure you understand is that the mutual inductance is really what's driving all of this in terms of the changing voltages from one to the other, in terms of the primary to the secondary and so on. But quantitatively, the self-inductance ratios are what determines these. So the ratio of the peak voltages and peak currents in the primary and secondary circuits is determined by the ratio of the number of turns in the primary and secondary coils. This latter ratio is called the turns ratio of the transformer. So we've got these two equations. We can consider two cases when the secondary coil has more turns than the primary. Then you'll notice that V2 is going to be larger than V1. And so we have the case then that the peak voltage in the secondary circuit is larger than in the primary circuit. We call this type of transformer a step-up transformer because it increases the voltage of an AC signal. So notice that in the step-up transformer, that the peak current in the secondary circuit is less than the peak current in the primary circuit because of the inverse of the number ratio here. So if this is larger than 1, this will be less than 1. And you have to have that in order to conserve energy. For a step-up transformer, the I2 will be larger than I1. If the secondary coil contains less turns than the primary, then the peak voltage in the secondary circuit is less than the primary circuit, so we call that a step-down transformer. Just like we would conclude in the other case, it changes the relationship between I2 and I1. If we have a step down, then the primary has more current than the secondary. So let's go back here. In the case where it's step up, the current in the primary is less than the current in the secondary. So let's take a simple example. Here's the equations that we just derived. Imagine that we have a resistor on the secondary, so therefore we will have I2 non-zero. We have our turns N1, N2 here. We're given those turn ratios, or the numbers for those turns, and we're given the resistance. We're going to imagine that we have a variable V1, and what we want to do is have I2 be determined, so we're going to have a particular I2, and find V1 and the resulting I1 that comes about in order to supply this current. So again, this is variable V1. We want a particular fixed I2 when we're done. The parameters that are going to be determining that will be V1, and we'll get an I1 out of the solution. To get this desired I2 through R, we can just use Ohm's law again to get V2 is equal to I2 times R. But V1 and V2 are related by the ratio N1 over N2, and so we can substitute in our V2, which is I2R. This is equal to V1. We've determined V1, so that's the first part of what we're supposed to do. But how about I1? Well, remember that I1 is related to I2. The ratio of N2 to N1 determines that connection. If we have a I2 in R, that determines V2, V1, and I1. So we've got then the I1 that we wanted to determine. We have V1 up here, so we have the solution to this particular problem. But we didn't say which was bigger. It could be either way. Just realize that if you have N1 larger than N2, it's stepped down. So that means whatever V2 you determine from Ohm's law here, if it's stepped down, this has to be larger than this voltage here. If you do it the other way around, so that you have step up, then to get that same voltage, which is required to supply I2, if it's step up, then this can be smaller than V2. It depends a lot on what this circuit is doing, and if you want V2 large or V2 small, whether or not you step up or step down. A typical case would be where this is 110 volts out of the wall, and this might be something that you want to have safe. So for example, somewhere around 15 volts, then obviously you want step down. Let's go back here where we have step down. We've already said that V1 is larger than V2. That's what we mean by step down. And so the result is that the current in the primary is smaller than the current in the secondary. And that's just the inverse relationship between the way the voltages change and the way the currents change. Don't forget that this resistor and this current was what determined this whole problem. You start there, found a V2, therefore you found a V1 in terms of the turns ratio. And then from that, you can then determine I1 immediately from this equation here. Let me say it more correctly. Once we have the current that we want and the resistor is fixed, that determines the voltage V1 that will supply that current. And of course that depends on this turn ratio. I1 is just simply the I2 that we desire with this turns ratio. Repeating then, the desired I2 and R determined V2, V1, and I1. The rest of this has to do with is it step down or step up. So next time we're going to be talking about energy, the energy stored in magnetic fields.